Welcome back, AP Physics to the Simkins Physics Corner. It's Mr. Simkins today with radian, revs, and ruh-roh right here. Last time we talked about the introductory terms for circular motion. But today I want to show you some samples of problems you might see for circular motion. Let's look at the first one. We got a steel drum rolled along the floor of a warehouse. If the drum has a radius of 0.4 meters and makes one complete turn every 8 seconds, how long does it take the drum to roll a distance of 36 meters? So for this problem, there's a couple things you need to know. Look at this phrase here. It makes one complete turn every. That is big T, or period. So big T is our variable for period. Now, if you look on your physics equation sheet, all the way down here, there's a bunch of equations for period. We're only going to be looking at this one today. I call it the trifecta, a triple equation, if you will. These are for later for oscillators. But this period equation, T equals 2 pi over omega equals 1 over f, the equation that we really need to be comfortable with. That's the first thing. You need to know what period is. How long does it take it to roll 36 meters? So how long? Well, let's see what we know here. We know the radius. We know how often it makes a turn. So let's go ahead and try to use that big T equation. That big T equation says 2 pi over omega. Now, if we do a little flipperoo here, we can calculate the angular velocity of the steel drum, right? That's omega, the angular velocity. So omega here is 2 pi over period, and that means our omega here would be 2 pi divided by 8 seconds. And so we put in our calculator, that will get us omega. Now remember, omega, the units here are radians per second. The units are going to be radians per second. So if we do our calculation, it turns out that omega is 0.785 radians per second. Now you might say, well, Mr. Simkins, how does it tell me how long it takes to do this? Well, we don't know yet. But what we do know is last time we were together, we said that the velocity of the center of mass of a wheel that's turning or moving or rolling without slipping, as it might be said, the velocity is going to be equal to omega r. This was a big equation that we established last time. Velocity is equal to omega r. If you're not sure why that equation exists, you can go back to our last lesson and watch that one. But we did come up with this identity. And so that means that our linear or translational velocity can be calculated by doing our 0.785 radians per second times our radius, which is 0.4 meters. And if you look at those units carefully, it's going to be radians times meters over seconds. In this case, the radians kind of just go away. And so 0.785 times 0.4, that's going to be a translational or linear velocity of 0.314 meters per second. And you're like, Mr. Simkins, why are you solving for all this random stuff? Well, we know the distance and we know the velocity. And so since velocity is displacement over time, that's the final step. We know that velocity is equal to displacement over time. We can resolve that algebraically for t. That would be delta x over v for time, and that would look like 36 meters over 0.314 meters per second. That would be our time. And if we do that, it's going to be quite a large number because this thing is rolling pretty slow. So that's a typo there. Times, sorry, divided by, that's why I was wrong. Divided by 0.314. That's going to look like 114.6 seconds. So in this first example, we see the necessity of remembering V equals omega r. This guy's going to show up a lot. We also see where on the equation sheet our period equation is located and how we can use period or frequency to get to rotational velocity, omega. Let's look at another example. A soccer ball rolls without slipping. So again, if it says rolls without slipping, that's telling us that V is equal to omega r. It says that the diameter is 32 centimeters. So right away, before I even continue, I always assume that AP students can convert centimeters to meters, but that's not always a correct assumption. So just to remind you, 30 centimeters, you put a decimal over 2 places, that would be 0.32 meters. The equations in our rotational motion stuff are in terms of radius. So we divide the diameter by 2 to get the radius of 0.16 meters. It says we're traveling at a linear speed of 2.4 meters per second. Now, if you're not sure what that means, well, consider the units, meters per second. That's our linear velocity or our tangential velocity along the outer edge of the wheel, which happens to also be the translational velocity of the center of mass of the wheel, as we talked about before. That's your V. Your omega, again, you're rolling like this. You have some radius r. Through how many revolutions has the soccer ball turned as it moves a linear distance of 15 meters? So what I'm going to do for this problem is I'm going to start in linear world and see what I can find out, and then I'm going to go into rotational world. The reason I'm starting in linear world is because I want to know how long this is doing this for. So V equals delta x over t, just like we did in the last problem, t is going to be equal to delta x over v. And the delta x we already know is 15 meters, and the velocity we already know is 2.4 meters per second. So right off the bat, I can figure out how long this thing was taking its little journey across the ground, and it was 6.25 seconds. So that's nice to know. But the thing is, it says through how many revolutions. So it's asking us how many times did it roll over. Now, when we talk about variables, the amount of times it rolled over is going to be written as delta theta. If you can imagine a circle, I'll draw it up here. Imagine a circle. If we were to measure the angle that you sweep out, that would be theta, right? So theta is some angle inside the circle. Well, imagine you just kept keeping track of all that as you rolled and rolled and rolled. Delta theta is going to represent our angular displacement, or how many times did we spin over. Now, this standard unit is going to be in radians, so at the end of the problem, we'll have to turn the radians into revolutions. But let's see how this plays out. So since it's rolling without slipping, we know V is equal to omega r. That means omega is equal to V over r, which means that our omega here is going to be 2.4 meters per second divided by our radius, which is 0.16 meters. And our omega for this problem is going to be 2.4 divided by 0.16, or 15 radians per second. Again, remember that omega is in radians per second. Now what, Mr. Simkins? Well, we know the omega and we know the time, and just like velocity is linear displacement over time, angular velocity is angular displacement over time, which means that the change in theta, or the angular displacement, can be found by doing omega times t. So here we do 15 radians per second times t, which we already found to be 6.25 seconds. And if we multiply those together, we're going to get quite a large number. 15 times 6.25. That delta theta is going to be 93.75. And you notice we were in radians. So the final step, and if you go back to our last lesson, we did some examples of converting rotational units. The 93.75 radians, you would multiply that by rads on the bottom to annihilate, and you'd have revs on the top, because that's what we want to go to, and 1 revolution is equal to 2 pi radians. So basically, you're dividing your answer by 2 pi. Now, when you do that, make sure you use parentheses, because your calculator likes to mess up things when you plug pi's into it. But 14.9 revolutions is going to be our answer for how many revolutions has a soccer ball turned as it moved a linear distance of 15 meters. So another example where we see the importance of V equals omega r, and now we start to see the similarity between a linear equation and rotational equation. Let's look at another one. We talked in the last 2 lessons about this idea of centripetal force. So if you were on a gravitron, this is that ride where you spin around and your back is to the wall, and the wall pushes you towards the center. What this means is that the normal force is actually the force acting towards the center. We can say that the normal force is the centripetal force. What is the centripetal force? It's the normal force. Now, this tells us that we're going at a rate of 20 revs per minute, which is gross, because I almost said revs per second, because that's what I wanted in. So let's go ahead and just do that real quick. 1 minute is equal to 60 seconds, which means that our frequency in its proper units would be 0.33 revolutions per second. That might come in handy later. The radius of the gravitron is 5 meters. So here's where we're going to get a little fancy. Let's take a look. FC is equal to MAC. We talked about this in the previous lesson. If you go in your equation, right under the friction equation, there's the equation for acceleration. It says V squared over R. That means I can right? And then now we see that the normal force is the centripetal force, which also happens to be equal to mv squared over r. All I did there was a substitution. I would invite you to commit to memory that centripetal force is always mv squared over r, because that's always a true thing. Now, of course, there's other forces happening here, right? We're not sliding down, so something has to be keeping us from sliding, because, of course, gravity is acting on us. Well, that something would be friction, as hinted in the problem. What's the coefficient of friction necessary to keep the riders from sliding down the wall? And what we can see from this free body diagram is that gravity. Well, that's convenient, because we know that the force of gravity can be calculated by mg, and we know that the force of friction can be calculated by mu Fm. So I'm going to rearrange this because the problem is asking us to find mu. So why don't I go ahead and divide both sides by the normal force? And here's where I get stuck, because I don't know the mass of the rider and I don't know the normal force. Let's go back to our original expression now. mv squared over r. So watch this magical substitution. See this right here? That's equal to Fn, right? So that means what I can do is I can say mg divided by mv squared over r. I just made a substitution from our centripetal equation into our vertical equation. Now, of course, the masses cancel, and this cleans up pretty nice. We have gr over v squared. The r comes up because it's divided by r, so that goes up to the top. And mu is going to be equal to gr over v squared. But you say, Mr. Simkins, I know g and r, but I don't know the v. I don't know the tangential velocity. Well, let's talk about that. The tangential velocity can always be found by doing distance over time. You just said that, Mr. Simkins. That's not what you wrote. You wrote 2 pi r over period, which I did. That's correct. And we also know that the period is 1 over the frequency. So the tangential velocity can be found by doing 2 pi r f. We've done this derivation in the first lesson of this unit. So if you don't know what just happened there, you can go back and check that out. But Vt, the tangential velocity, can be found by doing 2 pi r f. So what does that mean? Let's finish this up. Mu equals gr over, all right, now our v is this right here, 2 pi r f. But that whole thing is squared. So 2 pi r frequency squared. So that's going to be gr over 4 pi squared r squared frequency squared. So I'm going to do a little calculator magic to give you that answer. And bam, 0.46 is our mu, coefficient of friction needed to keep the riders up on the wall. You can pause the video, check out the math there. What if we have a different kind of centripetal force, like this one? Well, if you spin something around like this, there's going to be a downward force of gravity, but something is pulling it up. If it continues to spin and not sink down or raise up, something has to be balanced. Well, it turns out that the string is pulling with some Fty, and it's also pulling with some Ftx. We can all agree that the string is pulling both to the left and up. This question is asking us, what's the speed of the ball? Well, let's jump into our equations. We know that Ft must be balanced with Fty, and we know that the Ftx is acting as the centripetal force. Look, this is towards the center of this circle that the ball is traveling. So let's unpack this. Because of the angle they give us, look at this horizontal piece. All right, this is our Ftx. That's actually opposite of this angle. And if it's opposite, that means we have to use sine, right? Because of the OH of SOHCAHTOA would tell us to use sine. So in this case, Ftx is actually Ft sine of theta equals, and remember centripetal force, memorize this equation, mv squared over r. On the other side, Fg equals mg, and Fty is going to be equal to Ft cosine theta. Y component like this is actually adjacent to the 73 degree angle here. What I'm going to do is I'm going to solve for Ft in this equation. Ft equals Fg divided by cosine theta. And I'm going to substitute again. I'm going to take this, because that's what Ft is equal to, and I'm going to plug it into this equation. What does that happen? What happens when I do that? Mg sine of theta over cosine of theta equals mv squared over r. Well, this is cool because the masses cancel, right? And I don't know if you guys know this or not. Maybe you do. G tan theta, right? That sine over cosine would be tan theta equals v squared over r. Now the question is asking us to solve for v, so I'll go ahead and do that. We got gr tan theta, and so I'd have to take the square root of both sides. The v would be square root of gr tan theta. The last tricky piece of this one is that they gave us the length of the rope, but if you label that correctly on the diagram, it's actually that, right? This is going to be the radius. So this is 1.63. That's the hypotenuse. This is the opposite side relative to the 73 degree angle is the radius. So if you did the trig for that, the radius would be equal to 1.63 sine of theta, or, and what we do here is we do the r is the radius times sine theta gets us our radius there of 1.56 meters. That goes in for the radius, and if we plug in all our values, we're going to get 7.07 meters per second. So there's one more example I want to show you. You guys got to tune into the next video because my 15 minutes is about to get cut. But I want you guys to be familiar after today with E equals omega r and this idea of what is the centripetal force. Fc equals mv squared over r, but it can be many different types of forces. So check out that next example. I'll see you next time with the physics corner.